Hello everyone and welcome to my second video on Benzyne Mechanism. In my earlier video, we had a general discussion on the mechanism of this reaction, and in this video we are going to see some applications of Benzyne Intermediate in organic synthesis. Before that, let's have a quick recap of what we have discussed in the earlier video. Aryl halides are less reactive to nucleophilic substitution reactions, and we have studied that the reactivity can be enhanced by carrying out the reaction under high temperature and pressure. Introduction of an electron withdrawing group at ortho and para position of the aromatic ring can also enhance the rate of the reaction. And further, the use of a strong base can enhance the rate of the reaction of aryl halides. When an aryl halide like chlorobenzene is treated with a strong basic amine in liquid ammonia, it gets converted to aniline. The reaction proceeds through the formation of benzyne intermediate. Now, what are benzyne intermediates? Benzyne intermediates have one additional bond between the two carbon atoms. The additional bond is formed by lateral overlap of the two p orbitals formed by the elimination of HCl. The new bond lies at the side of the ring and has little interaction with the pi electron clouds of the benzene ring. Therefore, the additional bond is weak and hence benzyne intermediates are very reactive. Benzyne mechanism are also called SNEA mechanism because in this mechanism there are two steps. The first step is elimination followed by addition. It is also called sine substitution because the entering group takes up the position adjacent to the leaving group, and this can be proved by isotopic labeling studies. Now, after knowing all these things, the common question that comes to our mind is, what is the use of studying this reaction? What is its application? Now, let's have some examples. Example 1, when para-bromotoluene is treated with sodamide and liquid ammonia followed by treatment with phenyl acetanilide, we get two products. One is major product and the other one is a minor product. Now, what are those two products? Now, look at the substrate. The substrate is para-bromotoluene. So it is an aryl halide. Now, aryl halides in the presence of a strong base like sodamide and liquid ammonia, it gets converted to a benzyne intermediate. Now, this is the benzyne intermediate, and when this benzyne intermediate is treated with sodium phenyl acetanil, this is a nucleophile, and this nucleophile attacks the benzyne intermediate to give two carbon ions. One this and the other one is this. So now look at these carbon ions. Are they equally stable? No. This carbon ion is more stable than this. Why? Because here we have a methyl group. Now, what type of group it is? It can donate electron. It has a plus I inductive effect. Now, the further the carbon ion from this electron donating group, the more stable is the carbon ion. And so, which carbon ion is more stable? This carbon ion is more stable than this. So, this carbon ions, when after protonation, gives rise to this product. Now, which product will be more stable then? This product will be more stable than this. Let's look at the second example. Fluorobenzene has to be converted into 2-phenyl benzoic acid. How can we do so? You can pause the video, think about it, come back and look at the answer. Well, now fluorobenzene is an aryl halide. It can be converted into benzyne. So let's see how can we convert the benzyne intermediate to 2-phenyl benzoic acid. We can do this by treatment with phenyl lithium in excess, followed by treatment with carbon dioxide and acid. Let's look at the mechanism of the reaction. When fluorobenzene is treated with phenyl lithium, we get a benzyne intermediate. This benzyne intermediate on treatment with carbon dioxide, before that, this benzyne intermediate, when you treat with phenyl lithium is already present in excess. So this benzyne intermediate is attacked with pH minus. Please note that this phenyl lithium is an organometallic compound. So organometallic compound have completely different reactivity. From this phenyl halide, we can get lithium minus and L plus. Why? Because of the electropositivity of the metal group. So this phenyl minus attack the benzyne intermediate and we get a carbanion here. This carbanion attacks the carbon dioxide that is present in the reaction mixture, and then we get the carboxylate ion. The carboxylate ion on further protonation gives 2-phenyl benzoic acid. Example 3. We want to convert orthobromoanisole to this benzyclobutane derivative. How can we do so? Yes, this is also a aryl halide. Can't we think of benzyne intermediate? Of course, this aryl halide on treatment with sodamide and liquid ammonia give rise to this benzyne intermediate. Benzyne intermediate on treatment of this compound gives rise to the anion. This anion is in close proximity with the C double bond O, and further the oxygen, which is electronegative, is having a positive charge on top of it, and so the negative charge will readily attack the C double bond C, so that the oxygen becomes neutral. The electropositive oxygen having the positive charge gets converted to the neutral oxygen, and this is the driving force for this cyclization. And what do we get? We get a ketal and a benzyclobutane derivative. Now we want to get this, we don't want this. So we know that ketals on acidification gives rise to ketones, and therefore we finally reach to this compound which we wanted to synthesize. Let's look at example 4. Here also we want to make a benzyclobutane intermediate, and through a benzyclobutane intermediate we want to synthesize this compound. So how can we get this compound, a benzyclobutane, this derivative from this compound? Again, this is an aryl halide. So Can we think of again a benzyne intermediate which will lead to this compound? Yes, let's see. When chlorobenzene derivative like this is treated with sodamide and liquid ammonia, we get this benzyne intermediate. This benzyne intermediate, when treated with sodamide and liquid ammonia, is already present in the medium, and this leads to the abstraction of the proton here, which is acidic, because this proton is adjacent to a cyano group which has an electron withdrawing effect. This makes these protons acidic, and since we have a base, a strong base in the medium, this proton is abstracted. This acidic proton is abstracted by the base, and this leads to the formation of the carbanion. Since benzyne intermediates are also very reactive, this carbanion attacks this benzyne intermediate, leading to the formation of this carbanion. Finally, this carbanion abstracts a proton from ammonia, leading to our final product, this. Let's look at the last example. Yes, we want to synthesize this compound, and we have a starting material with us. One of the starting material of the with us is this, and other starting material is ethyl acetoacetate. Now this ethyl acetoacetate has an active methylene group. Why is this? Which is the active methylene group? This is the active methylene group. What is it? Now active methylene group, why is it called an active methylene group? Because this methylene group is flanked by the 2 carbonyl group. And because of the electron withdrawing effect of these 2 carbonyl group, these 2 protons are acidic. It can be easily removed by the base. Let's look at the mechanism. How can you react to these 2 compounds and get this product? Now in this starting material we have a TMS group. This TMS group can be easily removed by fluoride treatment, and once this fluoride TMS group is removed, we get a carbanion here. This carbanion will lead to the formation of benzyne intermediate, because this OTF group is a good leaving group. Let's look at the mechanism. See, the fluoride group gets abstracts the silyl group, and as soon as the silyl group is abstracted, we get a benzyne intermediate like this, as the OTF group leaves easily, leading to the formation of benzyne intermediate. Now I showed to you that this ethyl acetoacetate can easily give rise to this carbanion because it has a active methylene group. The active methylene, this carbanion now attacks this benzyne intermediate, and we get a carbanion here. The carbanion here then further attacks the carbonyl group which is in close proximity, giving rise to the anion on the oxygen. Now what happens? This anion returns back, leading to the breaking of the cyclic product, giving a carbanion here at this, which is further protonated to give this final product. That's all for today. If you like my video, please subscribe, like, share and comment. Thank you and bye bye.